Yes, hello. I'm Rachid Yazami from KVI in Singapore. And today I would like to present my work on the revolutionizing the battery charging technologies. So this is the outline of my talk. I will first make a brief overview on the existing charging protocols for lithium-ion batteries and show the limitation of the constant current CC-based technologies, and then introduce the new technology that we developed, NLV, nonlinear voltammetry, fast charging, show some results and discuss and go to summary. So the most common charging protocols are summarized in this slide, where we see that most of the protocols from A, B, C, D, and E, they all have a constant current step. So the most common one is the CCCV, constant current, constant voltage, on the top left hand. And then in the middle, we have the multi-stage constant currents. And then we have a combination of constant currents and the pulse charging in D. And then the boost charging, and then the voltage trajectory, which is not a constant current. This is the only one that doesn't have a constant current. Okay, but the most commonly used charging method now is the multi-stage constant currents, where we apply series of currents, I1, I2, I3, etc. As you can see here in the red color, stepwise, and then the voltage is limited to at the end of each stage to a limit which is around 4.2 to 4.3 volt commonly. So this is a typical constant current profiles for CCCV and at a two-stage constant current profile. This is very common, and I think most of the people are acquainted with these two methods. In the right hand, the multi-stage constant current, here it's two steps. You can see that we have applied two successive currents to different C rates, and then we measure the voltage to some limits, and then we apply a constant voltage. It's like a multi-stage CC and CV method. And this one enables us to charge in about 1 hour for most of the batteries. Recently, there have been a review paper published in e-transportation on fast charging. And I would like just to summarize the conclusions of this paper. If we want to charge a battery in less than 1 hour, the issues that have been raised in this paper is heat generation, lithium plating on the anode, materials degradation as a result of gradients of lithium within the anode and the cathode. And in less than 1 hour, we cannot have 100% change in the state of charge, and reduced of the cycle life if we charge too fast. And also, it raised safety and thermal runaway issues. So this method is not, using constant current, cannot apply for charging time, full charging time in less than 1 hour. So the EV typical charging times for different charge stations or levels. So we have the type on the left hand of this table, level 1, 120 volt. This is the one that you have at home. If you are in the US, or level 2, which is the same if you have 2040 volt as in Europe. And then the last one is the fast charging, the direct current fast charger system that go to 480 volts. So the charging time here is actually between 12 to 18 hours for the first one, 4 to 6 hours in the second one, and then up to 60 minutes in the last one. However, for the last one, in 15 minutes, as I said, or 60 minutes, you cannot fully charge, I mean, from 0 to 100%. And the last column shows actually the cost of these chargers, between 10 to 1,000 US dollars for the level 1, to 20 to 50 $1,000 for the DC fast chargers. Now, as you may probably know, Tesla has the V3 supercharger of 250 kilowatt, and I took this slide from a report on testing Tesla S3 type battery car, Model 3, using the 250 kilowatt supercharger of Tesla. And the conclusion here is that the system can give 50%, from 0 to 50% state of charge in 13 minutes. And but it took another 28 minutes to reach 80%. And then from 80 to 100%, it takes another 33 minutes. So the total time is much higher than 1 hour if we want to go from 0 to 100% state of charge using the 250 kilowatt supercharger, V3 supercharger of Tesla. Now, the problem with the fast charging is actually to address the EV driving range, which is an issue. So today, most of the electric vehicle cars can provide up to 300 kilometers per charge. However, the users need to extend this range to over 300, like 400 and 500 kilometers. But this can go with an increase of the weight of the battery pack. And this is not a good solution because with the increase in the weight of the car, the amount of watt hours you need to drive every kilometer will increase. So the efficiency will be much lower. So the solution now is to find ways to charge batteries in less than 1 hour, if not in less than 30 minutes, so as to enable to extend the range of driving a car, an electric car. So the EV industry needs ultra-fast chargers, which is below 30 minutes. And this is what I would like to present today, our technology based on the nonlinear voltammetry, which is a solution to fast charging, as I will show in the next slides. So just a brief introduction of nonlinear voltammetry as compared to linear voltammetry. I think linear voltammetry is very common in a method in electrochemistry, where actually the time derivative of voltage is a constant. Whether you are increasing or decreasing the voltage during a cycle, the slope is constant. In the nonlinear voltammetry, however, the time dependence of time derivative of the voltage is not constant, and it depends on many parameters, including the current, the voltage, the current derivative versus time, the state of charge, the state of head. So this is a little bit more sophisticated protocol, nonlinear, but the most important is how to control the change of the voltage versus time during the process of charging, knowing that dV over dt can only be positive or zero during a charging process. So we have developed our own protocol and install it in our TurboCharge demonstrator. As you can see here, we show an 18650 cell connected to the demonstrator, and the demonstrator has current, voltage, and temperature probes, and we just need to push the button, the white button, and start the charging according to the time that's the target time. So first test, we started to charge in 1 hour. So this is a typical charge and discharge profile during 2 cycles of a battery that is around 4 ampere hour capacity, charging in 1 hour, and a discharge in about 1.5 hours. So what you can see here is that the voltage profile looks like stairwise increasing. However, the current is not constant. For each step, the current tends, of course, to drop, and then we increase the voltage, and next step, so as the current will increase again. And this is typical profile of nonlinear voltammetry charging in 1 hour. The details is here. This is just how the current in blue and the voltage profile look like during the charge in 1 hour using NLV. Now we reduce the time to 45 minutes, and we have a similar profile. Very important thing is that the current profile is changing according to the state of health or state of charge of the battery. And also within 2 different cycles, the current profile will, and the voltage profile will be different when we use NLV. This is one of the characteristics of this method. Now we go to 30 minutes. So you can see actually now we have some white columns here between, which means that we apply a rest time between 2 current pulses. They are not real pulses because the current is not constant, but still we have a rest time between 2 currents, and then we go to the next step and so on. So the protocol here, the most important thing is when we have to go from one voltage step to the next voltage step. And this is part of the protocol that we have developed. Now 20 minutes. So this is the typical profile of a charge in 20 minutes. You can see that here we needed like 1, 2, 3, 4 voltage steps, but this is not necessary. The number of voltage steps can be larger than 4 or 5. So it depends actually on the battery chemistry and the state of health of the battery. So anyway, we were able to charge the battery in 20 minutes. And we even pushed the limit to 10 minutes, but this time we have used the lithium iron phosphate based battery to go to 10 minutes charge. So this is the profile. And you can see actually that all the profiles are somehow all alike. We have the voltage plateaus and the voltage steps. And then the current is dropping, and we have this rest time between the 2 current pulses. We went even lower in charging time to 6 minutes. And here we have a profile for an LFP cell, which we charged in 6 minutes only. And I think we can probably claim that it is a world record for fully charging a battery in 6 minutes. Now you may ask the question, how about the temperature during fast charging? So this is a typical temperature and the C rate profile for charging in 20 minutes. You can see that the temperature, which is in red color, doesn't exceed 33 degrees C, 43 degrees C. And in most cases, the temperature remains below 40 degrees C. But anyway, it is below 45 degrees C in all cases that we have tested in batteries that are NMC type or metal oxide type cathode materials. Now for the NLV in 6 minutes, temperature remained below 50 degrees C, which is in the safe side of the LFP-based batteries, where stability can be assumed up to 60 degrees C. So we are at least 10 degrees below the safety limits of LFP-based batteries. We also applied the NLV to a set of batteries, organized in a series and in parallel. So here the typical voltage measurements of the cells. So we have used 200 milliampere hour LFP cells for doing the parallel, and also same for series. And we were able to charge the battery in 15 minutes for the cells in parallel. And so you can see here the cycle profiles during charge and discharge. The blue color is the current, the red color is the voltage, and we could achieve more than 200 cycles because the cycling is still continuing. If we accumulate all the cycles that we have been doing on these cells, it's over 400 cycles. And you can see that the capacity is almost flat versus cycle life, cycle number, around 800, which is 4 times 200 milliampere hours. Now for the batteries in series, we also applied the NLV successfully, and this is the typical current and voltage profile of the charging in 10 minutes. And we also did up to 200 cycles using this technology on the cells in series. Now for cycle life, this is also very important. This is a typical cycle capacity profile for an NLV charging in 25 minutes of a battery of about 2000 milliampere hours initial capacity. It is an NMC type cathode material, and the discharge in 85 minutes, which is the silver 2 or less than silver 2, silver 1.5 rate. And with this profile, you can see that we achieved over 1300 cycles, and the capacity dropped below 20% of the initial capacity. So now it's important to actually, in order to compare the performance of batteries according to the fast charging, we have to define so-called what I coined as the performance and the index phi, which is a sum over the all cycles, the cycles from cycle number 1 to the final cycle, to the discharge capacity versus the nominal capacity, the whole divided by the charging time, total charging time. So this is important because we have many claims of charging in very short time, but we don't know what is the cycle life, and we don't know what is the increase in capacity during the charging time. So at least we can define something that is normalized, and we can compare the performance of batteries according to this index. So in the case of the previous slide, the index as we calculated is about 2,800, and I would be very happy to compare this with other performance in the claimed by companies who have different fast charging technologies. Okay, so go to the summary here. We have developed a new nonlinear voltammetry protocol, which is safe and long life charging. And we could use ultra fast charging, UFC, in 6 minutes. It's possible in LFP-based batteries, because we know that LFP is a very fast cathode, and during the charging in 6 minutes, temperature never exceeded 50 degrees C. The other very interesting characteristic of NLV is that we can exceed the voltage limit of 4.3 volt. In some cases, we go as high as 4.6, 4.7 volt. But battery, because the time that we apply that high voltage is very short, so the battery is not affected much by applying a high voltage in very short time. So that's another very important characteristic of NLV, is that we are exceeding what is considered as the voltage limits for charging of metal oxide cathode-based lithium-ion batteries. We believe, this is our vision, that the NLV might put an end to the constant current based and more than 100 years old technology for charging based on the constant current. So we think this is probably going to revolutionize the charging technologies in the future, because number one, we can charge in very short time, the temperature is controlled at the cell level, and also cycle life is there because we exceeded 1300 cycles, and we think that we can even increase the cycle life even higher than 1300 if the charging time is around 30 minutes. We can exceed the 1300 cycles. We think that the NLV is number one suitable for the EV, electric vehicle or electromobility industry in the future, where the charging time is becoming an issue because we cannot increase indefinitely the energy density of lithium-ion battery packs. So now the best of the packs may have less than 200 watt-hour per kg at the pack level. So we don't want neither to increase the weight of the batteries embarked in a car. So this NLV technology will enable actually to charge very fast. After maybe every 300 kilometers drive, the driver can stop, go for drinking a coffee or wash hand and so on. And then after less than 15 or 20 minutes, the battery is fully charged. Okay, I would like to say thank you to my co-workers, Professor Douglas Maskell and Mr. Srivant from NTU. They are both of computer science engineering departments of Nanyang Technological University. And with this, I would like to thank you very much for your attention. I will be happy to take questions. Thank you very much.